Hey, Sean, what's going on? You only play basketball, you're really upset.
Pelkey keeps giving me these alkenes that I gotta make, and I don't know what to do.
Well, we gotta do the Wittig reaction.
The Wittig, huh?
Come on.
Okay, so the overall mechanism of the Wittig reaction is you start with this alkyl halide. The part of the key of the alkyl halide is this halogen group, which for now I just have as a chlorine, but can also be a bromine, iodine, or OTS. And then that's used to prep the halide. So it creates this halide intermediate, and then that is used alongside a ketone or an aldehyde to make the alkenes. So for the mechanism, the first thing that we have to do is actually make the halide. So electrons on the phosphorus attack the carbon where the chlorine is attached and kicks off the chlorine. And then this implicit hydrogen here, that's not drawn here, is then removed by base and makes this double bond on the phosphonium. And then this double bond then, through resonance, separates the charges. That is ideal. Then with the separated charge that we have from here, we want it to attack the aldehyde. And then after it attacks the aldehyde, the charges go to the O-. And there's actually two forms of the Fischer projection that is used for this model. So one of them has no steric hindrance, and that's the major form. The other one has steric hindrance, which makes it a minor form because it's a slow reaction. So the sterics here on the minor reaction is due to this R3 group being so close to this phosphonium group. And so this steric hindrance causes it to be a minor form, whereas if the R groups are on the same side, like in the major group, not a lot of steric hindrance makes a major product. So then this Fischer projection is just redrawn here as a more normal looking molecule to make it easier to do the mechanism. But for the sake of explaining why there's a major and a minor form, I had to include the Fischer projection. So the electrons from the O then attack the phosphonium group and make a cyclic structure, and then the cyclic structure does a rearrangement to kick off the phosphonium group and make the Z alkene major form with the R groups on the same side. Same idea in the minor form, however, the R groups are on different sides, and then that makes a E alkene minor form.
All right, Aiden, I'm starting to get it now. But what if, let's say, my R group's an ester?
Oh, well then it'll be a Horner-Wadsworth-Emmons reaction.
Oh!
Okay, so for the Horner-Wadsworth-Emmons reaction, similar to the Wittig, however, instead of having the Wittig R group, where it's just general R group, that R group is specifically an ester, shown here. So this ester still has an R group, but compared to the Wittig, I drew it the same way as the Wittig, but squaring in the what would be considered the Wittig R group to show the difference between the Horner-Wadsworth-Emmons and the Wittig. Same idea, you're still adding the phosphonium, adding base, adding the aldehyde to make two different alkenes with selectivity for the E or Z. So for the mechanism, same idea to get to that phosphonate intermediate, having the phosphate bonded to the alkyl halide. So we have the base, attack the hydrogen makes a double bond, carbon-carbon double bond, and the electrons then go up to the oxygen. Electrons come back down, double bond makes the alpha carbon have electrons, give it that minus charge, and that was through resonance. Then I have this molecule just come down to the middle for sake of simplicity, and this is where it splits into the two different ways it can go about the reaction. So the first way I want to talk about is the major form, which is on the right. So both ways are considered fast. So this is not where selectivity occurs, unlike the Wittig where it is actually sterically hindered, and that's what makes the major and the minor. This is sterically hindered. However, this is the major form and considered similar speeds to the other one. This alpha carbon electrons attack the carbonyl center. Electrons move up to the oxygen, give it that O-. Then this O- attacks the phosphate, and electrons move up to the oxygen on the phosphate. And so this makes a cyclic ring structure, and that way is slow because of the R groups. So usually the R groups are rather long, and that gives it that E preferentiality due to thermodynamics. However, if you use small enough R groups, like the example given in the textbook was methyls, then it would actually prefer the Z, and there's also different modifications like the Stojanari modification that can make a preferential Z. So makes this cyclic ring structure, rearrangement, and it makes the E alkene. So for the minor form, same idea, having this alpha carbon electrons attack the carbonyl center, move up to the oxygen. Oxygen attacks the phosphate. Electrons move up to the oxygen. However, this is considered slower, and this is where the selectivity occurs. And the cyclic ring structure is formed, rearranged, and it makes the Z alkene due to this R group being towards, and this one being away, makes the E versus the Z, and that's where you get the regioselectivity. So now that Sean has done some Wittig and Hornwise with Evans reactions, let's see if you can determine which one this is. So Sean, what reaction would that be?
That's the Wittig reaction.